Are you excited? Are you very much excited this term is going to be over soon? Yes, yes. Okay. So as you probably know, this is the last module we have. Last set of a module I like to go through, that's the simple linear regression. You probably have, I trust you guys have already watched the videos and also watched the extra long walkthrough video I made for you guys. Okay, and so I'm going to go over quickly some of the key concepts from this module, and then we're going to start working on some extra practice problems for you guys. Right, okay, so let's start. So simple linear regression, it is very important to know when to use a simple linear regression. Simple linear regression, okay, so I'm going to ask a bunch of questions, right? Okay, so simple linear regression, okay. So I'm going to start with the regression technique. So the regression, there are three words, as you can see, simple linear regression. So regression is the word I'm going to focus on here. Regression is a kind of a technique that's able to help us to examine any kind of a relationship between some x's versus some y's. So the x's, some of the textbook is going to call them explanatory, x's they call it explanatory variable. Okay, I'm going to write it out of here. So those are very important things. So this is very important. So regression, it talks about a relationship between x and y, right? Between x and y. So the x here represents the explanatory variable, And the y, what is the name called for y? Do you remember there are different names we talk about this class? What is y called? What is the y variable called?
Is it the dependent variable?
Dependent variable. Okay, okay. So yes, so it's a dependent variable. I'm gonna write it down here. Dependent. Okay, unfortunately I'm running out of space. Okay, dependent variable. Okay, so the first part is the regression word, right? This is the regression. Okay, so where does the linear part come from? What does the linear here mean? What does it mean about the relationship between x and y? This should be easy.
It means that they correspond with each other, like they go in the same pattern.
They go same pattern. Yes, that's right. I think when you say it goes same pattern, that means it is a positive. Okay, so I need a little bit scratch paper here. Oh, hold on a second. Okay. So linear here means, okay, the relationship between x and y is straight line. Okay, so what I just draw here is a positive linear relationship. It could be also a negative relationship, right? Okay. On the other hand side, if one, I think Amy was saying, so they go with each other. So that means one goes up, the other one also goes up. This only means they are positive. For example, the pattern, the trend of this relationship can follow a non-linear relationship. So as you can see, the curve I just draw, this is not a straight line. Okay, as axis goes up, that means go from the left to the right, you can clearly see the y also goes up as well, right? As you can see, x goes up, y also goes up. So this only means it is a positive relationship. This doesn't mean this is not linear. This is clearly a trend. There's some kind of a curvature to it. So it could be, some other people call it exponential or maybe concave, but this is not linear. So as far as linear relationship is concerned for this class, we are only focusing on the relationship between x and y is a straight line. It could be a positive one. It could also be a negative one, right? Okay, okay, good. So the next word we're going to focus on here is going to be the sample. So I mentioned a few times in the slides, what does the sample here mean? What does the sample here mean? What does the sample mean here? What does the simple linear regression? So sometimes we want to compare simple linear regression with multiple linear regression. So you want to differentiate. What's the difference between simple linear regression versus multiple linear regression, right? Okay. I'm gonna explain the difference between simple linear regression versus multiple. So multiple means the number of x's you have, or maybe the explanatory variables you have in your model, are going to be more than one. It could be 2, it could be 50, it could be 1,000. Okay, versus for simple linear regression, you only have one x, just one x, right? Regardless whether we are talking about simple linear regression or multiple linear regression, the number of y, the response variable, or maybe the dependent variable, is always one. Is always one. If you have multiple y's, you cannot use the linear regression technique. You cannot use the standard linear regression technique, right? Right. Is this part clear how I explain the difference between simple versus multiple linear regression?
Yeah.
Okay, good, excellent. Okay, so what I did here next on the handouts is you're gonna see two tables here, two tables. I would highly recommend you guys to put these two tables in your note card because these tables are not included in the formula table that's provided to you during the final exam. Okay, I also want to stress, as you can see on the second table here, there's also a Anova table. Do you remember we also learned about another Anova table last week? You probably remember it. There's another table we learned. It's also called Anova table last week. That Anova table is different from this one. As you can see, I put it here for linear regression. The previous Anova table we discussed, it was for comparing multiple population averages. Remember the example we did is we talk about, the passenger satisfaction rating. If you take the first classes versus the economy versus the business class, so you're comparing their satisfaction score. You try to compare multiple population averages. You also have to build a Anova table, which is different from this one, They look somewhat similar, but not the same. Okay, if you're not sure the difference, I would highly recommend you to copy both tables on the note card because I've already taught this class many years. I know students typically thought they are the same one, so they just copy one in their note card. That's not a good practice, right? That's not. Okay, great. So I'm going to go over them quickly because this is important. I'm going to use the structure of these two tables to answer some of the questions on the handouts. Okay, so let's take a look. So what do we have here? The first one is a coefficient table. So typically coefficient table, it has an intercept, it has a slope. Hopefully you remember what is called given from the notes. So typically I like to use a beta 0 for intercept, whereas a beta 1 for slope, right? Okay. In BA 375, you guys are going to learn multiple linear regression. When you have multiple linear regression, as some of you were telling me, there are going to be multiple x's, right? So you're going to have x1, x2, x3, and x4. Okay, so for x1, you're going to have a beta 1. For x2, you're going to have a beta 2, and so on and so forth. For example, if you have xm, you're going to have a beta m. So that's why over here, I like to use beta 1 because we only have one slope, right? Okay, so what I just written down here is for 375, but I like to be consistent whenever I talk about linear regression, regardless whether it's simple or multiple. Okay, so what do we have here is a table, and we have the estimate given here, the estimate. So if you watch the video, you probably remember this is going to be called the beta 0 hat, how we estimate it. And this is going to be called the beta 1 hat, right? Okay. Some other textbooks like to use a different notation. I'm just going to put it down here. Hopefully it wouldn't confuse you very much. So instead of putting beta 0 hat, some textbooks like to put a B0 or maybe B1, right? They are the same. They are the same. I know it's a little bit confusing, but I like to point out to you in case you see different notations here. Right, okay. So there are also a column for standard error. Okay, so typically the numbers you get in this table, they are estimated using software. It could be Excel stat, it could be some other software we have. Okay, so for the standard error we have here, okay, That's going to be just standard error of beta 0, right? This is just going to be standard error of a beta 1 hat. Okay, so those are pretty straightforward. Okay, what we have next in the next column is the t-statistic, right? Okay, if you watch the video, you probably know the relationship between these 3 columns are that. So the t-statistic, this column, is just the ratio between the estimate and the standard error. So if you do have this quantity, you divide it by this quantity, you are able to get a t-statistic, right? You do the same thing for here as well. Use this cell divided by standard error is corresponding standard error. You're able to get a t-statistic, right? Okay, if you remember what we did, whenever we talk about t-test, t-statistic is your test statistic. Based on your test statistic, we should be able to figure out the p-values. Okay, so how am I going to figure out a p-value? How would you figure out a p-value?
Wait, I have a quick question. So
yes,
it's estimate over the standard deviation of the error?
Standard error. Standard error.
Oh, just standard. Okay.
Yes,
okay.
sorry. This is a standard error. Okay.
Okay.
Okay, I'm going to change this. This is just a standard error, right? Okay, got you. Yeah, you are absolutely right. I like to use STD to stand for standard deviation, right? You probably remember that. Okay, good. So, well, it looks like I think I made a mistake here. I should not include this column here. I'm not sure why I did that. Okay, so as you can see, the answers are given here. The p-value, I was asking the question, how you find the p-value? You're gonna use the F. Okay, sorry, I'm terribly sorry. This is gonna be the t-table, right? Okay, so my bad. I'm gonna change this. I'm gonna update, revise these documents and post a revised version on Canvas later on. So this should be t-table because we are talking about t-statistic, as you can probably see. So this is a t-table, right? Any questions here? Questions?
What would be like?
Yes.
So would the degrees of freedom be the n minus 1?
Excellent, very good. So you probably remember for t-distribution, there's a degrees of freedom. That's going to be just the sample size or the number of observations you collected minus 1. Yes. Okay, where did you get a degrees of freedom?
Are you talking about like on the table?
Yes. You just said n minus 1, right? Okay, so did you say it is n minus 1, Amy?
Yeah.
Where did you get that?
I was wondering if it was. I wasn't sure.
Okay. Where did you? Okay. Do all of you agree it is n minus 1? I know this part is really tricky. If you watch the video, you probably know something I was talking about. Okay. So do all of you agree it is n minus 1?
I think that's n minus k minus 1.
N minus k minus 1, right? Okay. So this is related with key question number 3. And as you can see, we are doing a t-table here, t-table. So the degrees of freedom is n minus k minus 1, where k represents the number of x's included in your model. Just like I said earlier on, for simple linear regression, this is always 1. So that's going to be n minus 1 minus 1, so n minus 2. Okay, so that's an excellent point that you guys raised. And so I'm going to change this one. Okay. So it is n minus k minus 1, right? If you were wondering what k is, if you go down this handout, you can probably see here. K refers to the number of x's. It is always 1 for simple linear regression because the number of x's we used for simple linear regression is always 1. Otherwise, we will call it multiple linear regression, right? Great. Okay, so the next table we have is Anova Table. Again, this is different from the one we covered last week. This is useful. This is the table set up here is for linear regression. The numbers somewhat similar to what we had last week, but they are not identical. That's the key. Okay, so let's take a look. Again, we can split the variation, the differences you see in your data into 2 different sources. The first one is going to be the model, the regression part. And the second one is going to be the error part, which is not explained by our model, right? So I want to differentiate. So the first one is the part that can be explained by your model. That means can be explained by your X. And the second one, the residual, means the amount of variation that cannot be explained by your model or cannot be explained by your X. Okay. And we have SSR. Last week, I think it's called SSTR. Here is called SSR versus SSE. You also have their corresponding degrees of freedom here. Again, they should add up. Those two should add up to n-1 here. And the mean square is fairly similar to what we had last week. You just use the sum of squares column divided by the corresponding degrees of freedom column. You're going to get MSR. Mean squares, right? You're able to get MSR, MSE as well. So MSE, this quantity given here, is an important quantity. Why do I say that? Why is MSE important? Do you remember anything we used MSE for? Do you remember anything we can use MSE for? When are we going to use MSE? I think this is related with key question number 5 from this week. When can you use MSE? What is the key question number 5? It is related with how good our model is, right? You develop this linear regression model. You do want to make sure it works really well for our data. So we want to evaluate, we want to assess our model, how good it is. MSE is one criteria we can use for simple linear regression assessment, right? Okay, so MSE is related when we assess the model, when we assess the goodness of our model, the goodness of our model. Okay, I'm gonna ask you several other questions here. What other ways to assess how good our model is? Can you give me some methods to evaluate how good our model is? So I've already said MSE is one way to do that. What some other ways to do it? There are 4 ways in total, 4 different methods. Besides MSE, mean square of error, can you think of any other ways? Okay, there's a metric we learned. I think it has a squared term to it. What is it called? Okay, it's called R squared. Anyone remember that? R squared, right? Okay, super important. R squared is one way to tell whether your model is good or not. Okay, so how, we prefer a model with a higher R squared. So how high is going to be considered high?
1.
Yes, 1 is absolutely considered high because R squared is always between 0 and 1. So the highest R squared we can ever get is 1. But a lot of times we don't have R squared to be as high as 1. If it's at least 70% or 0.7, right? We will consider that's an excellent model. That's a good model. Okay, so the third one is F ratio. So F ratio is actually related with this Anova table we set up here. So once we do set up this Anova table, we are able to calculate the F ratio as what we did here. And based on this F ratio, we are able to calculate its corresponding p-value. And then we are able to carry out an F test, right? So this is going to be F ratio F test. Okay, so if you do have a very high F ratio, that means a very small p-value, you are going to reject the model. Sorry, you're going to reject the null and claim the model is useful. Okay, so the very last method we have here is known as a residual analysis, which involves going over a bunch of applause from your residuals, and you're going to check whether 4 assumptions are met or not. So those 4 assumptions are known as LIN. Okay, so the line assumption.
Linearity, independence.
Yes. And normality and also equivariance. Excellent, excellent, Jackson. Thank you. Okay, good. Make sure you guys check them out. So 4 different methods to see whether our models are good or not. Mean square of error. We prefer a model with a small MSE. I think all of this being indicated clearly on the PowerPoint slides. We prefer a model with an R squared that's at least 70%. Sometimes 60% is good enough as well, right? There's no clear cut, but it really depends on your discipline. If you're from marketing, you may have a different set of R squared that you need compared to another physicist from a department of physics, right? Okay, and the third method we have is you are going to use an F test, which involves setting up this Anova table. And the very last method here involves going through a bunch of residual plots. And what we are doing there is we try to see whether the residual analysis is good enough or not, right? Okay, so let's take a look. So some other notations I'm putting on here, I've already mentioned N refers to the sample size, the number of observations you used in your data. And the next one we have here is just a relationship between those three quantities. The SSR plus SSE always give us the SST. That means if you do have 2 out of those 3, you should be able to fill in the rest, the missing one, right? This is fairly similar to what we did last week as well.